All right. I was trying to think of something that's not normally distributed, which isn't hard to think of necessarily, but I want it to be relevant. And I decided to go with loss of smell for COVID. So sorry, let me get my pen on. There we go. So loss of smell if you have COVID. So by now, a lot of us have either had it or know people who have it, or have had it. And I would argue that most people don't lose their smell, right? Their sense of smell. And so if we were to go out and survey, say, 20 people and ask, did you lose your sense of smell? How many days did you lose your sense of smell? So lost smell. And if we would make a histogram, so we have the frequency, I think most people would have 0 days of loss. Personally, I've had COVID, I think, twice, and I never lost my sense of smell. But my girlfriend, she had COVID and she did lose her sense of smell for about 2 or 3 days. So, anyway, I think if we went out, we'd sort of anticipate kind of this shape here. And I don't know how far off it tails to the right. I think some people lost it for like a year. I don't know for sure. I can't remember off the top of my head, but probably go pretty far. But I bet most people get it back within like say 2 weeks. Maybe over here is 14. Um, and so it's kind of rare to have it gone for 14 days. And so when I draw this curve, what I'm trying to say, if you want to think of it, so this is sort of a theoretical curve, theoretical. And if you want to think of it in like a more practical or applied sense, what I'm saying is if you survey 100 people or something like that, then we sort of anticipate the histogram for loss of smell. So here's 0 days, and then here's like 1 day, and here's 2 days, and so on and so on. We anticipate the histogram to have this kind of shape, and it might not be perfect. Um, and in fact, so then there's also this idea. So in red, I've got some histogram from some data of a sample size where I'm pretending it's 100, even though I didn't label literally anything, so it doesn't matter. But I want to talk about the sample size for a moment and just, I want to show you sort of how hard it is, how much you need a sample to get an idea of the underlying distribution. So this theoretical curve, this curve is called a distribution. And you can think of it for this class as sort of the shape of your histogram, right? These bars, they're pretty thick. When I was drawing them, I was imagining them each being a day. But if each bar was a second, then it's sort of like, you'd have to fit like 1,000 bars or however many seconds are in a day, right? Whatever it is, 60 times 60 times 24. Um, we'd have all these little tiny bars and they would very closely like follow the curve, right? And that is sort of a theoretical idea. It's one of the ideas core to calculus. Let's switch to, so I tried to build some code for us. All right. Anthony from the future, I wanted to explain this a little bit better. So, um, this is what I was pulling up in the video, is my computer code. Let's run through what's happening. So, if indeed this blue curve does represent the true theoretical distribution of loss of smell for COVID, and it was a little bit easier for the coding purposes if I measure this in weeks. So this number one means 1 week is how often people lose their sense of smell on average. But that's very different than how often people you talk to lose their sense of smell, in the sense of if you go out and you talk to, say, 20 people, you might get the following data. So there's a person or a few people maybe who did not lose their sense of smell at all, which is kind of what we expect. Maybe this group of people where it was, about 2 or 3 times as big. So maybe this had 2 people and this had 5 people in it. I mean, we could figure this out. Well, I don't want to get in the weeds. And they all lost their sense of smell for like 1 to 2 days, right? And you see, okay, fine. But it'll change depending on the group of 20 that you ask. Okay, so this group of 20, only a couple people lost their sense of smell for more than a week. A lot of people, it's even less, right? So, okay. And you get it, so here the mode of this sample of 20 were people who did not lose their sense of smell at all. And then a couple of people lost it for like a day and so on and so on, right? Now, my bins, I did not break up these bins into sizes of 1 day. Um, oh, I could show you what that looks like maybe real quick. We got plot. Of course, I'm getting off topic now. Let's say bins. Okay, great. Um, so if we're going up 5 weeks, 5 times 7 is 35, and boom. Okay, great. So now this is more realistic where each bin is like you lose your sense of smell for a day. And so it looks like we happen to get a lot of people who lost their sense of smell for exactly a week. Run it again. Here, a lot of people lost their sense of smell for no days. Okay, so you get it. This is a histogram. I'm not collecting data, and my data looks wildly different with every sample, despite me having this theoretical curve. What does that even mean? So that's what I want to talk about. So now, I'm going to take away this bins part because that'll make it look. Oh well, okay. Let's see what happens. This is an experiment for me. Let's go. Let's take a sample size of 200. Okay. So what does this look like? Boom. And so now suddenly the distribution on how many days people have lost it for, this histogram for that, it does start to follow this curve a bit better. And what happens if we take an even bigger sample size? We talk to 2,000 people. Okay, and now the histogram is just matching that curve perfectly, right? And um, so this is what I mean when I say we have a theoretical distribution. I mean, if you go out and you take large enough sample sizes, and what large enough is depends on the sample and the distribution and all these things. Typically, if you get up into the thousands, you have pretty good data. So, it took 2,000 here. Actually, okay, again, I'm going off scripts. Let me go up to, so here's another, this is me goofing around. What if I can train the computer a different theoretical distribution? So this distribution, it, it becomes more likely as you go on and on and on. Maybe this is like the likelihood of death or something, right? You're more likely to die as you get older. I don't know. So again, uh, I guess this is with, yeah, a sample of 2,000, you can see it. But this, even that 2,000 is not as good as the previous 2,000, right? We need more for this distribution. Let me show you what 200 looks like. You can't really tell it's being pulled from that distribution curve at all. You can see the stuff down here is less likely, the stuff over here is more likely, but that is, who knows, right? For this, you probably have to go up to like at least 20,000. And now you can really start to see the true underlying theoretical distribution. So having a sense of the shape of histograms as you get more and more data, that takes a lot of sampling, right? And so there are limits to what we can do as a society if we're investigating something. But suppose I don't care about the overall shape and I just want to know what is the population mean. So let's go back. But if you just want to know the population mean, so on average, how long do people lose their sense of smell for COVID? It turns out it's about a week. Okay, so if you just want to know that, something you could do um, is you could go out and let's take groups of size 20. You sample 20 people, you take an average. Okay, how close is that average to the true population mean? I don't know. So let's go get another group of 20 and take another average. Let's go get another. In fact, let's do 10 groups of 20. Okay. So I'm going to generate that data and I want to show you how that data is generated real quick, at least at some level. So, okay, I've got my group size. So below when I call this function, my group size is 20, for example. Okay. And I've got how many different groups of 20 am I going to sample? Okay. So you don't need to know this is like the random number generator. That's what RNG is. This is me creating a spot to put all my data, but right now there's no data there. It's empty. Okay, but I have one spot for every single group of 20. Okay, so I'm going to go through all my groups of 20 and I'm going to generate the data. So what does that mean? It means I'm going to do this. So for each group of 20, I generate a random sample of 20. So I'm generating a histogram that looks like that, right? And it changes depending on the group of 20. You can see there's my different data, different group samples, right? Okay. And actually, here's a good sense to understand what's happening. So look down here, I have sample mean. For this particular sample on screen, my sample mean was 0.96. For this particular sample mean, it was zero point 0.9. Ooh, that's even further away from one. Not a good sample. For this one, 0.98. Oh, I got pretty lucky. I'm pretty close to the true population mean of 1, right? Okay, so each of those are samples of 20. And for every sample of 20, I'm just going to record the average of that sample. That's all that I'm going to do. Let me get back to, so here's where we were. Okay, so maybe instead of calling this M, I should say what it is. It's the group size. And so I'm going to feed that in. I have a group size Whoop. I have a group size of 20. Um, and then this is the number of samples. Okay, so or like the number of groups maybe would make that one. But so I'm gonna groups. So this is this groups. Um, so how many groups of 20 am I sampling? I'm sampling 10 groups of 20. Okay. I'll do it for one group first. The graph isn't going to look as pretty. And this is referencing all all this parts is referencing the same function and curve as before. So I really am just doing these groups of 20 and taking the average. That's all I'm going to do. Yeah, there we go. Okay. Okay. So this particular group of 20 had a sample of, I don't know, 0.83 or something like that. Let's do 10 groups of 20. Okay. Whoa, that is highly unlikely. That is wild. Okay, well, even in this crazy scenario, uh, I have 10 different groups of 20. And how many bars? One, two, three, four, five, six, seven, eight. Yeah, which makes sense. So I happen to get two groups of 20 that lied pretty close to the true mean. But otherwise, they seem kind of spread out. But notice, I'm never really that far away. How far away do I even get? Maybe zero point 0.3, right? Maybe this is 1.3, maybe this is zero point 0.7. So I'm like zero point 0.3 away from the mean. If I do bigger groups, so instead of groups of 20, I do groups of 200. Okay. That's going to suck everything in because now when I take an average of 200 values, the highs and the lows really just they cancel out because if you have a high, you're more likely to have a low if you sample 200, right? And then you get a lot of people in the middle. So what's going to happen is when I generate this and I get my histogram, all the values of the histogram are going to be closer to one. You'll see the range of X values, so to speak, get tighter, get closer to one. So let's run this. Boom. And so what's happening there is we're seeing, oh, of course, we're seeing the fact that for averages, the standard deviation of the average, so how much this plot wiggles, decreases like 1 over the square root of n. So this, right? So what am I trying to, my sample size, as I go from 20 to 200, I've increased by a factor of 10. My standard deviation should decrease by square root of 10, which is, we'll just say 3. Okay. And sure enough, on the previous screen, the faraway bars were somewhere around a distance of zero point 0.3 away. You can rewind the video and see for yourself. I went from about zero point 0.3 to like a 0.7, and now the faraway bars are somewhere around a zero point 0.1 type of distance away, right? This is almost 1.1, this is about 0.9. And so if I do it again, if I go up by another factor of 10, then I better get squeezed in by another factor of about 3, right? 3.5, maybe something like that. So this should start to, well, let's just generate it. Okay. And so now our far away stuff, the vast majority is within like 0.03, right? It's about a third of the zero point 0.1 distance. Okay. If that didn't make sense, that's okay. There's other stuff that I want to demonstrate and show you. So let's go back to, this is where I just take groups of 20. I'm taking 10 groups of 20. Okay. So um, what I want to talk about, right? Where did this histogram come from? I want that to make sense. So where this histogram came from, I I'm taking 10 groups of 20, and for each group of 20, all I do is take their average, and I'm just plotting that. That is literally what this code is doing in the background. This red curve is saying what we should get in theory. What's the probabilities in theory? How likely is it? How likely is it to end up in this bin over here that goes from like point, or sorry, 1.16 to 1.18? How likely is it to end up in that bin? This small of a number of averages, in this case it was 10 averages, 10 groups of 20, right? Each group is one average. Cool. So I have 10 samples. Let's go up to 100 samples. Okay, and you can start to see that curve. Let's go up to 1,000 samples. So again, when I say sample, that means I have to go find a group of 20 people and take their average. That's one sample. Right? And now we're starting to really get there. And by the time we get to 10,000, we should really see this normal curve sort of pop out. Okay. Um, so And then to demonstrate before what I was talking about, this curve sort of gets tighter. Every time I increase by a factor of 10, that x access spread of my data should sort of decrease by a factor of about 3, about 3.3, something like that. So instead of the tail being out here at like 1.7, um, I need to do a third of this distance. So this distance is zero point 0.7. A third of that is about a zero point 0.2, zero point 0.3, something like that, 2.5. So I expect this spread to go out to about here, about the 1.25. So let's see that. Hey, what do you know about 1.25, right? Okay. Um, so if you tuned out, here's what I want you to take away from this video. And we're not quite done, but to recap before you get to the last point. We need large sample sizes of the population in order for the histogram of what we get to look like what we would call the distribution of this thing. So this particular example that I made up is how long you lose your sense of smell for COVID. This graph is measured in weeks. The true average for the population is they lose it for about a week, even though most people you talk to won't lose it for any days at all. 0 is the most likely thing to happen. Right? Um, so we see that you need to have sample sizes in the thousands in order to start to see what this true distribution is. Okay. Now, if we just care about what is the average time people lose their sense of smell, if we just care about the location of this green dashed line, right? You could take a large sample size, on screen is 2,000, yeah, and look at the average of that sample and hope that you're close to the true population average. And indeed, you'll likely be close to it. What do I mean when I say you'll likely be close to it? Well, if I go here, if I look at samples of 2,000, and let's just take 10 samples of 2,000. So each sample of 2,000 people, I take the average and I see how long do they lose their sense of smell. And I do that 10 times. Okay, we get here. And you can see, even though we don't land on the green bar, all these samples are pretty close, right? The furthest away I get is like 0.03. Here's, right, here's 0.97. That's about a distance of 0.03. There's 1.03. That's about a distance of 0.03 away from the green dashed line. And so when you take averages, you're drawn towards the true mean. And we can really see that if I overlay these two plots. So that's the last thing that I want to show you. Pop-ups. In blue, we're seeing this graph. Okay, so the last one that I generated, which was this one, we're now just copying and pasting and putting it down here. Okay. The y-axis gets distorted. That's been the hardest part of this whole little coding project, is trying to figure out how to display the data in a way that makes sense. Because when you display what's called a probability density, you have to divide by the bin width, and it becomes sort of an issue where it sort of skews how things look. But what I want you to notice, so what I'm doing is I'm overlaying what is, so in blue is a sample of 2,000 people, and you sort of, it looks all like this, right? And so that sort of represents, I mean, if I regenerate different samples of 2,000, they're all going to look pretty similar. They're all going to look like the curve, right? That's what was special about 2,000. It was big enough to where this histogram looks like the curve. Okay. So um, that's what's going on here. Now plotted in orange is this plot. And you can get a sense of, even though these bars, these sample averages look far away from the true average, that's only because of the way it's plotted on this figure, right? I'm only going from 1 to 1.08. I'm not going very far. So if we have some perspective of how far away sample averages are compared to population samples, let me re-say that. A group of 2,000, you take its average, that average is pretty close to 1. Whereas if you just ask a friend, a single person in the population, how far did you lose your sense of smell? They're more likely to be way over here. They're way far away from the true population averages, because population averages, they have some lows, they have some highs, and they start to cancel out, right? I think I can make this look a bit better if I just change, if I take, let's take 1,000 samples. So now this curve, it turns out that it makes it look nicer over here too. And you can start to get a sense of, and again, this has to do with because I'm plotting density and there's some math going on behind the scenes here. But man, we really spike out, right? And this spike, now we can also see a better visual when I talk about the width of that spike behaving like a 1 over square root of n. So if I decrease my group size by a factor of 100, okay, I'm only going to sample 20 people at a time instead of 2,000 people, then the width where our eyes are drawn, that's probably about 2 sigma, and I just increase sigma by a factor of 10. Oh, let's think about it over here. Okay, so I haven't ran this code yet. So this width, okay, I guess this is pretty nice. On this level of scale, we can probably see about 3 sigma out. So 3 sigma, it's probably about 0.07, but to make the math easy, I'll say 0.06. And sigma is going to increase by a factor of 10 because I decreased my sample size by a factor of 100, and the square root of 100 is 10. So I should be going out to like a zero point 0.6 um, instead of a 0.06, right? This horizontal distance is going to increase by a factor of 10. And then similarly, instead of minus 0.06, I'm going to have minus 0.6. So that'll go out to like a 0.3, 0.4, somewhere around there. So let's see that happen. Okay, and indeed, about a 1.6, about a zero point 0.3, zero point 0.4. But again, have some perspective. Let's look at this compared to the population. Okay, so in blue are I sample 2,000 individuals, and that's that histogram. And then in orange, I go out and I just sample groups of 20. Okay, and I take their average. And every group of 20, that average is so much closer to the green line compared to if you just look at your blue data values. Blue data values are over the place, but when I average my data, I get drawn towards the true population mean. And I get drawn even better the larger my sample size is, the larger my group size is. So that's my group of 20. If I had a group of 200, I'm drawn even closer to the mean, which you can't see here, but the moment I run it here, okay, that the orange peak gets skinnier by about a factor of 3. So it's like 1 over 3, isn't it? Okay. Um, okay. So when I say the sample mean wants to be mu, when I say X bar wants to be mu, what I'm saying is no matter how this blue curve looks, if you sample some people and you ask them how long they lose sense of smell, if you sample some data, no matter what the population curve is like, when you take the average, the highs and lows cancel out, and your average value is going to be one of these bars in this orange histogram. And they're pretty close to the true mean, right? So that's all that I'm trying to say.
It turns out it's very useful to know, well, what is the average? So mu is the mean, right? For the whole population, for example, how long do people lose their sense of smell on average with COVID? That's a useful thing to know when the pandemic's first happening and we're thinking like, oh no, is this permanent? What's going on, right? So this is unknown, but what we can do is we can go take a sample and we can compute an X bar. We can compute a sample mean, okay? So this is a population mean. And the thing is, so the little mantra that is not mathematically accurate, but it gives you the right idea, is X bar wants to be mu. Okay. So what do I mean by this? So this distribution, this theoretical distribution, um, it has a formula. Don't worry about it. It's something like e to the minus x. Not going to quiz you on that. But it has a mean and it has a standard deviation. Okay. There are ways to compute this. They involve calculus and knowing this curve and stuff like that. Um, but if we sort of had these numbers in our pockets, okay, it turns out X bar behaves so well that even if I don't know this theoretical curve for the population, if I knew these values, I actually know exactly how our sample mean is distributed. X bar is distributed normal, where its mean, so if I draw a normal distribution, then normal distribution kind of looks like this. And again, you should think of if you take a lot of samples, this is the shape of your histogram, right? So we'd have some bars that tend to follow this kind of shape, and it might not be perfect. You might have kind of a tall bar over here, but overall, it would follow this shape. And as you sample more and more, it follows it better and better. That's what I was trying to show with my computer code, and more code is to come. So anyway, um, this this normal distribution, it's centered at mu, where I am talking about the mu from the population distribution. So how long do people lose their sense of smell with COVID? Um, if you go out and ask 100 people, a lot of them will say zero. Some of them will have positive numbers. Some of them will have pretty big positive numbers. Okay. But most of the people will say zero or one or something small, right? And so the big numbers wash out with some small numbers. And in fact, when I go from my data to my X bar, when I compute the average, X bar is definitely bigger than zero. It's definitely positive because if I ask people how long did you lose your sense of smell, they're not going to say anything negative, and they might say positive numbers. And the moment that we have a positive number, when we take an average, we have a positive average because I'm just adding non-negative numbers. They're either zero or they're positive. So it's going to be big, right? It's going to be bigger than zero. So X bar already is behaving way different than this theoretical distribution for single individuals. So we have this curve is applicable to the individual in a population. How long did you as an individual lose your sense of smell? It's very likely you will answer that question with a low number. It's very likely you'll be in this region. Okay. A different question. If I survey 100 people and I ask, how long on average do these 100 people lose their sense of smell? What I'm saying is, if you go out and get 100 data points, what's X bar going to be? X bar is not going to be zero. And in fact, X bar is going to have a distribution that looks like this curve, and it's going to be centered around the true population mean for this like theoretical individual up here. We can start to get a sense for mu by sort of graphing X bars, if you will, and seeing, we'll start to see this curve form. But we can be even more specific than this. The mean mu for our sample average, yeah, we tend to denote it with mu sub X bar. Okay. It's the mean of the sampling distribution is the way that we would say that. Quite a mouthful. So similarly, there's a standard deviation for the sampling distribution, and it's sigma over the square root of n, okay, where this sigma is this sigma. So the the distribution for the individuals of the population influence the average and what we expect to see. What I want, so when I say something like Z is distributed normal 0, 1, or Z is a standard normal distribution, I want you to have a picture in your head, right? And the picture that I want you to have in your head is this thing that I'm measuring Z, whatever it is. Okay, if I was talking about like height is a good thing to talk about because it'll have this type of curve, even though it's not normal 0, 1, it's normal something something, where we need to talk about like where the bump is and what this stretch factor is, right? So for a normal 0, 1 curve, the mean is 0 and the standard deviation is 1. And visually, we sort of look for this spot where the curve goes from concave down to concave up, and it should be symmetric about the mean. So it's going to be about here, about here. That's roughly about the same distance, right? And so that gives you a sense of where to put your plus or minus sigma. So plus or minus 1 in this case, because sigma is 1. And so when I say Z is distributed normal 0, 1, I'm saying if you go out and you sample from this population a lot, a lot, a lot, and then you plot a histogram, we expect to see bars that more or less follow this shape. And they'll follow it better if you have a big sample size. Okay? So what's truly amazing about the central limit theorem, and I will connect this to confidence intervals and stuff like that. Let me go back to sharing my computer screen. Okay, cool. So let's put these things together. All right. Um, when I say something is normally distributed 0, 1, then I want us to have this picture in our head where this first number is telling us where to center our normal peak, and this second number is telling us um, how wide that peak is, right? Because a peak that is not, or sorry, let me do a very broad peak. Okay. And again, you look for from concave down to concave up. Oh, it looks like it's about over here. And so this width is a sigma. Okay. Anyway, so it turns out averages, even if we don't know the underlying distribution for the population, if I don't know this curve here, right? Averages, we know the curves. Averages are distributed normally. Okay. So, um, an example that seemed to work kind of well in class is to talk about Instagram likes. Okay. So, what's the average number of likes per post? Okay. So, Instagram, they do know the true average. They know mu. Maybe I should use a different color for these like other bits. Okay. And they know sigma. So they know how many likes every single post has. They could compute the average number of likes per post. They could compute the standard deviation in likes per post. Okay. So if someone at Instagram were to randomly sample, like say 100 users, the value doesn't really matter. I could just say they randomly sample in users and then they compute X bar, but they don't stop at X bar. They then compute this thing because they work at Instagram. So they have access to this number mu, this number sigma, and so they can compute this thing here. So for example, um, maybe you have some really cool kids with some, a lot of likes per post, maybe had 10K likes, and then you have people like me who have 3 likes per post, right? And then all these other users and stuff. Um, and the highs and the lows, they start to cancel out. And you'll get one average. Okay. Maybe it was 5. I don't know. Um, and then maybe mu, the true population average, was something like 7. And so say 5 minus 7. And maybe the true standard deviations, I imagine it's a pretty big standard deviation for likes on Instagram. So maybe it's something like 10. I don't know. Right? It's what I'm trying to say, what I want to get at. I didn't want to circle mu. Oh no, there we go. What I'm trying to say is that this object is a number. Okay, it's just a number. And it's someone they could compute it at Instagram when they sample in users. And if it works better for you, imagine in your head they sample 100 users. Okay. This number is distributed normal 0, 1. And so when I say that, we can leverage some stuff here. And so for example, I know um, that 80% of the time, this number, x bar minus mu over sigma, lies between minus 1.28 and positive 1.28. Okay. Um, I know that 93% of the time, whatever. And how do we find these bounds? So let me walk through what I'm about to do here. Again, if we were to do this over and over and over, so each time I sample 100 users, I take the average, and then I subtract mu and divide by sigma, and I go through and I do that, and I plot all the different values that I get. I expect to get this kind of shape. And so because I fully understand this shape, I can ask myself, well, wait a second, what range contains 93% of my data? Okay. And so in other words, this area, because areas correspond to probabilities or proportions of your data and stuff like that, this area is 0.93, and I want to know where these little cutoff values lie. Okay. I'm going to choose 0.94. We'll make some of the other stuff a little bit nicer, a little bit easier. Okay. So in order to answer that question, we need our handy dandy calculator. I think it would, there we go. Nice. Cool. And let me go and just clear the screen real quick. So I'm going to go to my distribution window. I'm going to go down to inverse normal. Okay. And now if in green is 94% of my area, then, and I'm imagining this is symmetric. So this little bit shaded in red is going to be equal to this little bit shaded in red. And it's all the stuff that's left over. So I know, um, sorry, this 93 is bothering me. I want to also change this to a 4. I know that what's left over is 6% of my data. Ah, so down here must be 3%, and over here must be the other 3%. So if I want to find, for example, this value here, I could say, oh, well, the area to the left is 3%. And this is a standard normal. It's centered at 0. It has a standard deviation of 1. I'm talking about area to the left. I'm ready. I hit enter, and I find this value here. That value is minus 1.88. I'm going to stop there. Now, I could have also instead gone about this trying to find this point here. And I think, okay, how much area is to the left there? Well, you could do area to the left, or you could do area to the right, because area to the right is 0.03. So I go down here and I just switch this to the right. And there's that, okay? And it should always be equal and opposite. The normal distribution is symmetric, and we're looking at the symmetric centered 94%. Okay, so now I can say, oh, 95% of the time, this computation, x bar minus mu over sigma, lies between 1.88 and negative 1.88. And by the way, this is how I got these numbers. If, let's do it for the 80%, for example. If I were to draw a picture like this for 80%, then instead of the 0.94, I would do zero point 0.8, right? And so here's another way we could do it. We could do zero point 0.8. We could say, no, but that's the zero point 0.8 in the center. And if you do that, it'll tell you both numbers at the same time, right? And notice they're equal and opposite. It's one's negative, one positive, it's the same number. And that's where I got the 1.28 from, okay? All right. So because we know how this thing is distributed, we can say statements like this. 94% of the time, this number that we're computing is between plus or minus 1.88, okay? And it's because X bar, sample averages, we know a lot about. And in fact, if thinking about doing this computation is weird, we could instead say, well, look, X bar is distributed normal with mean mu and standard deviation sigma over root n. And then I'm just saying like we could bound X bar, but it looks worse than these numbers. Okay. And mm, I'm getting off topic. We can come back to that and connect it at the end. For now, uh, do you understand how we're getting these numbers? So for example, you work at Instagram, you randomly sample 100 users, you compute their average, that's how you got the X bar. You work at Instagram, so you also know what the true average likes per post is. And you work at Instagram, so you also know what the true standard deviation likes per post is. And so you can compute this, right? That number that you'll get 94% of the time is between plus or minus 1.88, for example. Okay? These cutoffs, they have a name, and their name is influenced by their area. So this value we call z sub 0 point or, zero point 0.03. Okay, and in general, um, if you are 1 minus alpha percent of the time somewhere, okay, we're gonna try to out 1 minus alpha confidence intervals. And in fact, this is the beginning. This is like a sort of like a 94% confidence interval. Okay. And so in this case, my 1 minus alpha would be 0.94. It's this area in the center that I'm talking about. Um, and so in general, uh, we're going to have this curve, this normal curve, and there's going to be some center area, which is 1 minus alpha percent, which means the leftover area, in order to get 100%, um, oh, oh, I should do 1 minus alpha equals our confidence percent or whatever. What I'm trying to say is the leftover areas, these things, they're the remaining alpha. They're what's missing. They're the alpha that's missing. And half of it is over here, and half of it is over here. And so the general name for this spot is Z sub alpha over 2. We see this show up, okay? And it's just the name for this spot right here where our region of interest, this thing, stops. And if you know one spot, you know the other because they just differ in sign, right? So this spot is negative Z sub alpha over 2, okay? All right, so because we know how this is distributed, we can say these bounding things. And from here, if you do algebra, you end up with a confidence interval. And so confidence intervals, they ultimately come from this idea of knowing how X bar is distributed. That's behind every confidence interval. So let's do the algebra. Oh, sorry. I was supposed to do that. Sorry. My computation all along has this little mistake. It should have been that. Apologies. Okay, so what am I going to do? I'm going to multiply everything. One different color. What else can I have? Sure, why not? I'm going to multiply everything by sigma over the square root of n. And so when I multiply over here, I have minus 1.88 times sigma over the square root of n. And when I multiply in the center, it cancels with the denominator. That's why I'm doing it. And when I multiply on the right, I have 1.88 times sigma over root n. Okay. And now I want to multiply by -1. So multiply by -1. And okay, so when I do that over here, it becomes positive. So I have 1.88 sigma over root n. And when you multiply by -1, you have to flip the inequality. And now mu was negative, so it becomes positive. And x bar was positive, it becomes negative. Flip the inequality, minus 1.88 sigma over root n. Okay, but now you know what this looks like. This looks like C is bigger than B is bigger than A. And so you can imagine to yourself like 3 is bigger than 2 is bigger than 1. And I don't like writing inequalities like this because normally I sort of picture a number line where it's so okay, again we have this. I like to think of it as 1, 2, 3. I like the low numbers to be on the left. And so if I just sort of flip everything over, I'm not changing what this relationship is. I'm just sort of changing how I read it. Instead of reading from sort of right to left, I'm going to read from left to right where it feels more natural. So I'm going to say minus 1.88 sigma over root n. This thing is less than, this thing, mu minus x bar, which is less than this last thing, 1.88 sigma over root n. Okay. And now I'm going to add x bar to everything. So let's add x bar. So we get x bar minus 1.88 sigma over root n is less than mu is less than x bar plus 1.88 sigma over root n. Okay. And voila, this right here is called a 94% confidence interval for mu. And 94% of the time, if you go out and sample n many people, or in many subjects, or in many Instagram posts, and you compute the average like or the average measurement of interest, an X bar, okay? And if you know sigma, then and you know your sample size, and so you do sigma over root n, then 94% of the time, this will be true, okay? So, that is the whole idea behind chapter 7.1, okay? Or section 7.1, I should say. 7.2 is a bit more realistic because here, I remember when we did all this, I said, pretend you work at Instagram, pretend you know mu, pretend you know sigma, right? It's much more realistic that we don't know mu and we don't know sigma. But the whole point of all this is to end up where you're bounding mu. And what you're bounding it by is an X bar. That's something you know. And then this other funky looking term, sigma you don't typically know. But if you replace the population standard deviation, sigma, so with the sample standard deviation, well, you know the sample standard deviation for the same reason you know the sample mean. It's your sample, it's your data. You know it, okay? And so it turns out this other object, and you might think, but I don't know mu. That's okay, just hold on a moment. This other object, this has also a well-known distribution. It's called a t distribution, okay? And guess what? It basically looks like a normal distribution. So I'm going to draw the same looking picture, okay? But this right here is a t distribution. And t distributions, unlike normals, okay? So, well, first off, they're always centered at zero, whereas at normals, we had the ability to move them around, like I could center him at some other spot mu, okay? And similarly, there was this like standard deviation stuff going on. T distributions are completely determined by your sample size, okay? Uh, they're determined by something called the degrees of freedom, but it's just your sample size minus one, okay? But in your head, I want you to just picture the normal curve, the bell curve, okay? It's got this bump, it's centered at zero, but it's a t-distribution, okay? And so then I can say stuff like 94% of the time, if I were to compute such a thing. So let's talk about the COVID stuff again. I sample 100 people, okay? And I go out and I compute the average days for the loss of smell. And so maybe I get like X bar is equal to, so I'm talking about days. So maybe it was like 6.4. And I have a standard deviation for my sample. And maybe that was something like 5.2 days, right? And okay, mu is something that I don't know. But nonetheless, what this type of computation would look like would be something like 6.4 minus mu over 5.2 divided by the square root of 100, aka 10. Okay. This number, whatever it is, and it's 94% of the time going to be between, is between. And so just like before, we can go over here. We can do second distribution, but now I want to go to my inverse t distribution. Enter. It says, okay, what area do you want? Okay, so here's the thing. I'm going to draw a very similar looking picture to before. We have this center 0.94 area, and say we'll do the spot on the left first because it's kind of easier. That means that I'm missing this other 0.03 area and 0.03 area. So with this function on the calculator, we don't have the options for left, center, right. It will only shade left. Okay. So if I put 0.03, I'm talking about the area to the left being 0.03. I'm talking about this spot right here. So what's my degrees of freedom? Let's pretend that I have a sample size of 100. So my degrees of freedom are 99 because degrees of freedom is just one less than your sample size. Okay. So that's what you need for this. So I go down and I hit paste and enter. Here we go. And okay, so this is minus 1.9025. I'll just do 90. Okay. So this must be positive 1.90, but let me show you how we would get that. So back to the distribution menu, inverse t. And so now the area to the left of this spot is this 0.94 plus this 0.03. So in total, I have 0.97. Same degrees of freedom because it's the same curve. Hit enter, hit enter. Oh, look at that. Equal and opposite, right? Okay. So that's how we'd find either of those two spots. And the name of these spots, because we're looking at a t distribution, we would call this t sub 0.03. It's the spot on the t distribution where you have that 0.03 area, this 0.03 area out in the tails. Okay. And in general, this area in here, we say there's 1 minus alpha, which leaves half your alpha on this side and half your alpha on this side. And in general, we call this t sub alpha over 2 for these kinds of spots over here. Okay. And now, even though I drew arrows to both, technically, I should only draw the arrow to that one. And for this guy, we do negative T alpha over 2. Okay, the positive number is what we're going to call T alpha over 2. So, okay, um, this value, this value, uh, x bar minus mu over s over root n, it's between, for example, 1.9 and negative 1.9. And if you do the same algebra we did before, or maybe I should just use this one, it's between 1.9 and negative 1.9. If you do the same algebra as before, we have to multiply the denominator. So I have minus 1.9, then I have 5.2 over 10, because the square root of 100 is 10, is less than 6.4 minus mu minus 1.9 times 5.2 over 10. And then I'd have to sort of manipulate this a little bit and massage it a bit, and you get mu is bounded between, and I'll have 6.4 plus 1.9, 5.2 over 10, and 6.4 minus 1.9, 5.2 over 10. Okay. And so right here, this is a 94% confidence interval that shows up in section 7.2. It's in the scenario where we have to use our sample standard deviation, which means we're looking at a t-distribution. Okay. But it looks so similar because it's the same kind of logic. It's just, the logic is we know the distribution for this type of normalized measurement or standardized measurement. And because we know it, we can bound it in that form. And you do the same algebraic manipulations. And so then you get something that looks very, very similar. The look of this, the look of this is I have this value here, which is x bar. X bar, I'm now going to either add or subtract. Okay, if I want to get the left or the right, so I add or subtract. And then there's some multiple whose name is T alpha over 2. Okay, and that's essentially counting standard deviations, but it's telling you sort of how far away to go to capture 94% of these values. Okay. And then the last final bit is this, which is called the standard error. Okay. But it's just the sample standard deviation divided by the square root of n. So sometimes I might say the term standard error. All right. And that's a confidence interval. That's the recipe, right? This is the recipe for a 1 minus alpha percent confidence interval. And I do have a slight abuse of notation happening because really 94% in this example is equal to 0.94 is equal to 1 minus alpha. Okay, there we go. So then that gives us alpha equals 0.06. Um, and so 1 minus alpha is not equal to the number 94. It's equal to the number 0.94. And so when I say 1 minus alpha percent, I'm technically lying. That's technically writing 0.94%, which is not true. It's not what I'm talking about. Um, but I think it gets the right idea across, so I do it. Um, anyway, cool. So what else did I want to say about this? Ah, right. So let's pretend. Oh no, yes, that's right. I wanted to actually compute these values real quick. So since I have that up, I can just say times 5.2 divided by 10. And so it turns out this product is equal to 0.989 blah blah blah. Okay, and let's add 6.4. And so then this number as a whole is equal to 7.389 blah blah blah. Okay. And what else? What else? What else? Let's subtract 6.4 to get back to where we were. Let's multiply this by -1. So now we're doing the subtraction part. And now I'm going to add the 6.4 back. And so this number here as a whole is 5.41. 0, 6, blah, blah, blah. Okay, fine. Okay, so what if instead I went to the stat menu, go over to tests, and what section 7.2 is all about is something called a T interval. So it's a confidence interval when what you're looking at, when your averages are best described with the T distribution, because you have to use a sample standard deviation. Okay, so an interval for a T distribution. So I'm going to choose option 8, and I'm in my T interval. In case that happened too fast, let me do it again a little bit slower, where I actually scroll down. I'm going to choose option 8. It says T interval. I'm going to enter statistics. It says, what's my average? 6.4. What's my standard deviation? 5.2. That's what I was using, right? Yes. What's my sample size? 100. What confidence level do I want? 0.94. Calculate. All right. And hey, don't those numbers look familiar? Huh, 5.41. And I stopped right after the 6, but I think it was like a 9 or something like that. It would have rounded up. So I have a 7 over here, right? And then 7.389, right? Okay. So this process is what the calculator is doing behind the scenes. Although technically the calculator is just doing this. It just jumps to, it knows, it's been programmed to know all this algebra ahead of time. But this is what a confidence interval is. We know how averages are distributed. Averages behave very well. Averages want to be, X bar wants to be mu. It's going to have this little peak around mu. And it's so predictable that we sort of know how to capture averages the majority of the time. And that's what's going on behind the confidence interval. Um, Anything else I want to say? No, yeah. Okay. I guess that's it. So one more time, since I spent a lot of time on this code, and I think it's just kind of fun. I just want to show you one more time that, if you go out and you take averages of, like, what did I have here? Was it 50 people? Oh, here it's up to 200, although it doesn't really matter. The magic number tends to be 30, so we'll do 30. I have to rerun this. Cool. So, versus if you just sample individual people in the population. So, this blue curve is sort of the theoretical distribution of days of loss of smell for COVID, or sorry, weeks of loss of smell. I changed yeah, whatever, to make it centered at one. So, 1 week tends to be about the average loss of smell on a population level. Um, but if you go and ask people, you'll sort of get stuff all over the place. And so, if you look at the blue histogram, it's not so clear that this is the theoretical curve. Now, if instead you go out and you ask groups of 30 people, how long did you lose your sense of smell? How many weeks? And you take the average of that 30 and you do it for multiple groups of 30, those data points cluster around the true average for that blue curve. They're really trying to detect it for you, right? And so that type of idea is what's going on in the backbone of all statistics. So, anyway, cool. Thank you. See you next time.